Great. Did you hit it?
Yep, it's all.
Okay. Welcome, everybody. Today's speaker is Anthony Sanchez from the University of Washington. He'll be speaking about gaps of saddle connection directions for some branched covers of tori. Go ahead, Anthony.
Thank you. And to kind of extend some of Dimitri's comments from before the recording, I want to say, thank you to the New England Dynamics Number Theory Seminar for, giving us a chance to see lots of people that we wouldn't have had the chance to see otherwise, and for, walking us through lots of different areas of dynamics and number theory, including the geometry of numbers, substitutions, algebraic dynamics, and homogeneous dynamics. And today we'll see a little bit of translation surfaces in my talk. So thank you very much for giving me the opportunity to speak. And yeah, so today I'll be talking to us about gaps of saddle connection directions for some branch covers of tori. And the hope is if you know none of the words in the title, at the end of the 45 or so minutes, you'll know all the words in the title. This work is on the archive. It's submitted and posted on the archives in case you want to look into it further. And yeah, so let's go ahead and get started. So as I kind of indicated, part of the work is related to translation surfaces. And so I want to start with kind of the simplest definition of a translation surface. And so by translation surface, I just mean a collection of polygons with edge identifications given by translations, essentially. So I'll walk us through a couple of examples so we can kind of understand what I mean by this. So maybe the first and most important example of a translation surface is given by the torus. So we take a square inside of the plane, glue the top to the bottom and the left to the right. And so topologically, we'll get some kind of donut-shaped surface that is a genus 1 surface, so with one hole, with kind of flat geometry everywhere. And what I mean by that is if you're standing anywhere on the torus, maybe you're sitting there watching me on your computer screen, and you get kind of tired during the talk, so you want to stand up and maybe stretch and do a little spin. Then if you start to spin, you stop seeing me and you spin, and you only have to spin around one time in order to get back to staring at me through your laptop. So that's what I mean by flat geometry everywhere. And so that's kind of example one. A typical second example is given by the regular octagon. So here I take the regular octagon and I identify opposite sides. So 3 glues to 3, 1 glues to 1, and so on and so forth. And in this case, we have a genus 2 surface, and maybe it's not immediate that it's a genus 2 surface, but one way to kind of see it is to kind of use an Euler characteristic argument. So Euler characteristic count. So 2 minus 2g is the same thing as the number of faces minus the edges plus the vertices. We see we have one face. We see we have 4 edges. And so we should count the number of vertices. And so maybe here's one vertex. It's the left side of 3. This is also the left side of 3. This point right here is kind of the bottom of 4. This point right here is also the bottom of 4. This is the top of 1. This is also the top of 1. Bottom-ish of 2. This is the bottom of 2. Right side of 3. Right side of 3. Top of 4. Top of 4. Bottom of 1. Bottom of 1. Top of 2 is the top of 2. And we get back to where we started. So there's a single vertex in front of us. All these kind of vertices reduce to the same point. And so we'll get -2. And so when we solve this equation, we see that g is equal to 2.
It's not quite -2 according to what you wrote, but maybe if you replace 3
sorry, there's indeed a, yeah. So it's the coffee still hasn't hit, I guess, right? So there's not 3 edges, there's 4 edges. Thank you, Dimitri.
Okay, it works now.
And so we get a genus 2 surface, right? So something topologically, so something topologically, a 2-hole donut. And we get a single cone point of angle 6 pi. And so my stylus seems to have decided to die. So let me switch the battery. A single cone point of angle 6 pi. And what I mean by this is if I'm standing at, the single vertex that we have here, and I do the same thing that I did earlier, right? These are all the same point. And you're staring at me through your laptop. If you spin around and try to see how many times you need to spin around in order to get back to seeing me, you'll need to spin around 3 times. And so that's what I mean by a cone point of angle 6 pi, that you need to spin around 3 times at this single vertex in order to get back to seeing me. And this is kind of a consequence of the fact that this is a higher genus surface and we're drawing a flat picture of it. So there's going to be kind of curvature somewhere, and with translation surfaces, we're kind of concentrating this curvature onto a finite set of points. In this case, just a single point. And so now the main translation surface that I'm interested in for this talk is given by what I'm calling a so-called double slit torus. And so I want to walk us through what I mean by a double slit torus. And so I want to take a flat torus and I want to mark 2 points on it. This is a very fancy way of saying grab your favorite parallelogram in the plane, glue the top to the bottom, the left to the right, and then go ahead and label 2 points on this parallelogram. I will always mark the vertex, call it dot, and now we can mark any point on the interior and I'll call it X. Okay. And so go ahead and take 2 copies of this twice marked torus, right? It's a torus with, 2 mark points. And go ahead, carefully cut a slit open between the two marked points as indicated here. And so now this opens up the kind of originally independent tori. And so I want to close them up. And the way I want to close them up is by gluing them, gluing the top of the left torus to the bottom of the right torus. So if I'm running around on the left torus, after I hit this slit, I pop out of the other torus. Okay. And this is what I mean by a double slit torus. Why double slit torus? Because I've taken a torus, I've doubled it, and then I've glued it along a slit. Okay. So maybe it's easy to see kind of from the flat picture that it's topologically genus 2, right? It looks something like this. So it's a nice genus 2 surface. And moreover, there's 2 cone type singularities of angle 4 pi, right? This 4 pi again means that I have to spin around twice to get back to where I started at 2 points. The 2 points, one of them is X, right? So if we do this for the last time, if you're staring at me through your laptop and you're standing at this point X, if you spin around, you stop seeing me, you cut through the slit, pop out of the other torus, come back here, pop through the slit again, and then finish up. So you've had to spin around twice in order to see me. So there's not two Euclidean balls about me. And the other point that has excess kind of angle is given by this vertex, the vertex dot. Okay. And so this is going to be kind of the main character of today's talk, these double slit tori. And so if you've never seen translation surfaces before, this is the only translation surface you need to worry about today. So why would one, be interested in double slit tori? They're a very natural construction of higher genus surfaces from a genus 1 surface. And we understand genus 1 surfaces very well from different viewpoints. So we can hope to utilize some of these techniques in this context too. Higher genus here, right, means just bigger than 1. Dynamically, they're interesting because they're the first higher genus surface with minimal but not uniquely ergodic straight line flow. And so I should credit Mazur here. This is a result of Mazur. And I won't define what minimal and uniquely ergodic means, but what it means roughly is if you're standing on one of these double slit tori and you run around in some fixed direction, minimal means that you'll kind of see everything on these double slit tori. And the fact that it's not uniquely ergodic means that you have a favorite torus. Maybe your left torus is your favorite torus. So there's spots you like to visit more frequently than others. And so this is really interesting because this phenomenon is impossible in genus 1. So already we're seeing some interesting behavior with double slit tori, right? This phenomenon is impossible in genus 1, but it's not true in genus 2 already. Geometrically, I'm interested in these because these are examples of translation surfaces. And so for me, that means I could do geometry on them, right? I'll kind of say some more of what I mean by this very shortly. So notice that I'm embedding these kind of double slit tori in the complex plane. And the only identifications that I'm making with them are by translations. Translations are holomorphic functions. So kind of the resulting quotient is going to be endowed with a natural Riemann surface structure X, right? So I can think about this as a Riemann surface. Well, what else is on the complex plane? DZ is on the complex plane. I'm able to measure, arcs. I'm able to measure lengths and angles of paths. And again, by virtue of the fact that all of the identifications here are by translations, and translations preserved, DZ preserves translations, I get a holomorphic differential on this flat picture here, right? So again, I'm able to use geometry using this holomorphic differential. And more generally, any pair x omega where x is a Riemann surface and omega is a non-zero holomorphic differential is a translation surface. So this kind of gives us a complex analytic way of thinking about these very geometric objects. And kind of, to go from this definition to the polygon definition that I stated earlier, we can kind of cut along a basis of relative homology. And again, for me, the holomorphic differential means I'm able to do geometry. I'm able to measure lengths. It gives me a sense of direction. Okay. And so broadly speaking, I'm interested in paths on doubled slit tori. So here's another example of a doubled slit torus for us to have in mind. And I'm not interested in every path on a doubled slit torus. I'm only interested in special paths given by saddle connections. And so by a saddle connection path, I just mean a straight line trajectory that starts and ends at a cone type singularity with no other cone type singularity in the interior. So again, for me, the universe of translation surfaces for today is just doubled slit tori. Straight means exactly what we means here. We have DZ on these surfaces, and there's only two cone type singularities. So here, gamma is an example of a saddle connection that starts from dot and ends at dot. Okay, and now we can use the holomorphic differential to get some notion of geometry. Associated to each saddle connection, we have the holonomy vector. Right, so here, this is a nice path on the translation surface, and I have a holomorphic differential. So I pair them up in the way they want to be paired up, and I'm able to get, kind of get a sense of direction for the saddle connection, right? So if I integrate gamma along this holomorphic one form, I'm able to get 4 plus I. And I think about this, we can think about this complex number or as a vector, and I think about this as a horizontal and vertical displacement. So assuming kind of the side lengths are 1 of both of these parallelograms, I see that I kind of traverse once, here, 2 more times in this direction, and then 1 more unit contribution of horizontal traversing when I concatenate the piece that goes through the slit. So I've kind of traversed this translation surface 4 times horizontally, and that's where this 4 comes from, and I've traversed it one time vertically. So that's where this 1 comes from. So using the holomorphic differential, I'm able to kind of understand the displacement of this saddle connection, the horizontal and vertical displacement of the saddle connection. Another example of a saddle connection is the one that just runs off the top of one of them, given by delta. So we can see delta here doesn't move up and down at all. We can see delta doesn't move up and down at all. So the vertical displacement should be 0. And again, assuming the length of this side is 1, we get that kind of the holonomy vector associated to delta is 1, 0. And there's lots of these saddle connections, right? If you're sufficiently bored, you can build lots and lots of them. Here's like a third one we can call epsilon. And there's many more. So let me collect all of the saddle connections on this translation surface. Let me collect all the paths that are saddle connections on this translation surface. And let me call that set lambda sub omega. All right. Well, I claim that generically, the picture that we get for these saddle connections looks something like this. And so again, remember what this means, right? If I kind of take one of these checks here, this is coming from a saddle connection path on the translation surface where I'm recording the vertical and the horizontal displacement. So this check means that there's some saddle connection with length, say with 1 in the horizontal component and 4, say, in the vertical component. And so why is this a good picture? Well, this is a good picture of the holonomy vectors by a theorem of Veach. Veach says that in general, the saddle connections of a translation surface are going to be discrete. And this is the reason why I only care about saddle connections, right? There's lots of paths in these translation surfaces, but by restricting just to the saddle connections, I'm able to get a discrete subset of the plane, and not just some arbitrary discrete subset of the plane, right? This discrete subset is kind of capturing the data of saddle connection paths. So this is why I'm interested in saddle connections. And one can notice that if I look at saddle connection paths of the torus, I actually end up with the integers, the primitive integers, but the integers essentially. And we've been studying the primitive integer, the integer lattice for hundreds of years now. And so now out of this kind of construction, we're able to extract a different discrete subset that carries a lot of geometric information that's generalizing kind of the integer lattice. So this is one reason why one may be interested in saddle connections. And so broadly speaking, this project is interested in understanding how random are the holonomy vectors, right? And so if you just kind of started listening in, well, that's okay. I'll give us a quick recap. What I'm doing with this kind of program, with this project here, is I'm taking a translation surface given by a double slit torus, something that looks like this picture on the left. And on this picture on the left, I'm interested in paths on it, paths that go from dot to X, or from X to X, or from dot to dot. So these are saddle connection paths, and associated to each saddle connection path, I can record the horizontal and the vertical displacement. Like this one goes horizontally twice and vertically once up. So it corresponds to this saddle connection here, where I've traversed 2 units horizontally and 1 unit up. And I'm interested in the collection of all of these holonomy vectors, and I want to understand how closely does this discrete subset resemble a random set. And of course, this is a mathematics lecture, so everybody here read the slide like this. What do I mean by random? And so I'm going to walk us through a couple notions of randomness now. So kind of a first maybe test of randomness is given by the angles of the saddle connection. So by angle, I just mean grab the saddle connection, grab the holonomy vector, and kind of project it onto the unit circle. This is all that I mean by the angle of it. And we can do this for all of the saddle connections. And we can ask about the angles of a translation surface. Are there any forbidden angles? Are there any kind of favorite angles for a translation surface? And so by work of Mazur, it turns out that the angles are actually dense on the unit circle. So there are no forbidden angles. And kind of a nice follow-up question is, are there any kind of favorite angles? You know, and by works of Vorbetz, angles are equidistributed for almost every translation surface. So again, I won't kind of precisely define this. This audience likely is very well versed with equidistribution, but it just means that if I kind of look at all of the saddle connections in some big ball, and I look at the angles of those saddle connections, and I ask how many of them land inside of, say, a small interval, then I'm only going to see a small amount of proportion of angles inside of this big ball as L gets bigger, bigger, and bigger.
Anthony, so just to make sure that we understand the terminology, in your definition of randomness, the integer lattice will be a random structure. Is it too?
Yeah. With this kind of first order test, this is telling us that this is going to be a random subset. And so this is one test of randomness. And I should actually mention also Eskin-Markloff-Morris. That talks about equidistribution for covers of lattice surfaces. I'll get into this definition later, because double slit tori are actually covers of the lattice surface of a torus. So their result shows equidistribution of angles in that context as well. So kind of piggybacking off of Dimitri's comment, maybe kind of this first indicates to us that saddle connections appear to behave randomly at first glance. Right? If we just take the definition of equidistribution, then this is telling us the integer lattice is random. But we're mathematicians, of course, and so we don't just want one test of randomness. We want multiple tests of randomness. And I want to teach us a little bit about a second test of randomness given by the gap distribution. So it's very common in mathematics where if you have an equidistributed sequence, this is kind of telling you at order 1, the sequence is random, right? Everything's kind of uniformly distributed, equally distributed. And what you want to do is take that sequence and look at the gaps of that sequence and study how random that set is. And this is what I want to do in this context as kind of a second test of randomness, as kind of a sanity check. And for dynamical reasons that I probably won't be able to get into today, I want to actually consider slopes of saddle connections as opposed to angles. But understanding one's not so different than understanding the other, right? We can go from angles to slopes by taking tans and arctans. And so understanding one is not so different from the other. So to just kind of formalize this, what I mean by slopes, I want to go ahead and kind of introduce this slide. So let's slopes up to radius r of the saddle connections denote the slopes that land inside of this purple region here, this 8th sector up to radius r. So this purple region is a nice compact subset of the plane, and the saddle connections are discrete by work of Veach. So there's only going to be finitely many saddle connections that show up in this purple region. Let me go ahead and order all of those saddle connections according to their slope. So by S sub 1, I mean the smallest positive slope given by this one. S sub 2, I mean the second smallest positive slope, the second positive slope, S sub 3, dot, 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 up to however many there are. And that's what N of R means. N of R is just the number of saddle connections that I'm seeing. So kind of in symbols, this set is just a set S naught, equal to 0, S1, dot, 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 in increasing order, all the slopes up to however many there are. That's what I mean by N of R. Okay, and let me just consider these slopes for now. If I kind of rotate the other saddle connections to land inside of this 8th sector, I can understand them separately. So for now, let me just restrict to this 8th sector. And actually, N of R, the number of slopes the number of saddle connections that we're seeing in this set is a very interesting question, right? And this was actually studied by Eskin Maser, and they showed that kind of N of R has kind of quadratic asymptotics. So we expect to see about R squared many points in there. Yeah. So again, by kind of the previous slides, the slopes are behaving kind of randomly. And so we want to go ahead and not just look at the slopes, but look at the gaps of the slopes. And that's why I set up all this notation in the previous slide, because now when I talk about the gaps of the slopes, I literally just mean kind of the difference of consecutive elements, right? The literal gap of slopes that I see there for however many there are. And of course, there's maybe some small issue here, right? As R gets bigger and bigger, the number of saddle connections that appear inside of this 8th sector are going to become more. And so this kind of slope difference is going to tend to 0 as I bring in more and more saddle connections. So as R goes to infinity, this quantity just goes to 0. So I want to kind of remember how big this gap is, at least at the level of the microscope that I'm looking at it in, right? At least I'm only looking at this up to level R. So I want to remember it up to level R. And so it's natural to scale up by the number of saddle connections that I'm seeing in that 8th sector at that level, which is R squared by the work of Eskin Maser. So now this kind of quantity here has a chance of converging to something interesting. And this is what I mean by the gaps of holonomy vectors. And broadly speaking, I'm interested in what we can say about the distribution of gaps. Okay. So let me go ahead and take the gaps up to radius R of these saddle connections of a double slit torus. Let me ask how many of them land inside of my favorite interval I. Let's go ahead and count them. Well, how many of them could have landed inside of my favorite interval? That's N of R by the work of Eskin Maser. So now I don't just want to look at all of the saddle connections that land in I up to level, the proportion of saddle connections that land in I up to level R. I want to look at all of them. So let me let R tend to infinity. This is what I mean by the gap distribution. So kind of informally, this is measuring the proportion of gaps in some interval I, right? Appropriately normalized gaps in some interval I. Okay, and I want to say, what can we say about this limit? What do we expect in general about this limit? So what we expect, we actually will draw some ideas from probability. So suppose that X sub I is a sequence of IID random variables that are uniformly distributed on 0 and 1. So I just take my favorite, I just take a random element between 0 and 1, and I call that X sub 1. I take another element randomly in 0 and 1, call that X sub 2, and then maybe I take one more and it shows up very close to the origin, and I take X sub 3. Well, this IID sequence is going to naturally partition the unit interval into gaps, right? Here I see 4 gaps, right? Maybe a better version of it is boom there. So if I take an IID sequence, I'm going to naturally partition the unit interval into gaps. And so an IID sequence has a natural notion of a gap set. And I could ask the question I just asked a slide ago in this context, in the context of what I would deem as a truly random kind of sequence, an IID sequence in 0, 1, uniformly distributed. So I can ask the same question that I did before, right? Grab the gaps of this IID sequence, ask how many of them land inside of my favorite interval out of how many of them could have landed in there. And in this case, it turns out to have an exponential gap distribution, which means as I let n tend to infinity, I can find the proportion of gaps in interval I just by integrating 1 over e to the x against that interval. So this is kind of our benchmark for what we mean by a truly random sequence. And so we can ask, do we get an exponential function in the context of double slit tori? And so kind of the slogan result that I want people to kind of walk away from is the gap distribution of almost every double slit torus is not exponential, right? So I kind of, this kind of completes, the story that I've kind of been building up a little bit. I start off with a double slit torus. And I say, let me look at paths in this double slit torus given by saddle connections, right? So here's like an example again, or the favorite example. of a saddle connection that traverses twice in the unit direction and once up in the unit direction. And I look at this kind of geometric set that's capturing this discrete set that's capturing the geometric data of paths on the translation surface. And I ask how closely does this resemble a random set? And in this context, I'm able to show that this gap distribution is not exponential for a generic double slit torus.
So do you have just a negative result, or there is a distribution that you...
So thank you very much for that question. That ties very nicely into the next slide. I can say more than this, right? I don't just have a negative result. I have a full-on density function given by this is the graph, but given by some function f that I have the graph of here. So unfortunately, I won't display the function f explicitly because it's a very nice elementary function that's piecewise analytic with 3 different pieces. It has discontinuities here, 1, 2, and 4. And kind of in between these pieces, it's a very nice, it's a bunch of nice elementary functions, but the formulas get kind of big. So I encourage you to look at the archive paper that I submitted to see what the actual formulas are if you're interested in that. But I won't do that to us, for the people on the West Coast this early in the morning by showing many formulas. Maybe I should do it because there's many of us in the East Coast, but I won't do it today. I will show us the formulas. Okay. And so what this, go ahead, Dmitry.
But the tail looks exponential.
It does look exponential. And I promise everyone, I did not plant Dmitry in the audience to ask these questions, so we'll actually get into the tail very shortly. That's a very good question. Thank you.
Okay. So can you excuse me for asking one more good question?
Oh, of course, no, please.
Will you tell us what is the picture for the regular torus and Z2?
I won't actually show you the picture for the regular torus, but
very fractions, right? So what
yeah, but I'll say some words about the regular torus shortly.
Okay.
Yeah. These are very good questions. Thank you very much, Dmitry. So yeah, this kind of slogan theorem that sorry?
No more good questions. That's fine.
And please continue to everyone to interrupt me. I think it's so nice that I'd rather be interrupted than have no questions, in a Zoom talk. That way it doesn't feel like I'm totally talking to a computer screen, So kind of my slogan theorem is a consequence of this theorem that says I'm able to find a full-on density function for a generic double slit torus where I'm able to find the proportion, right? This quantity on the left is kind of capturing the proportion of gaps that land in some interval I. I'm able to find this proportion by just integrating this density function f against that interval. And this picture on the right is a picture of that function f. Okay, and so as Dmitry suggested, we have this density function. Let's flesh out everything that we can out of this density function. And so a very natural question is, the tail of an IID sequence is given by is exponentially small. What about the tail in this context? Right, so what's the probability of me seeing a big gap? Well, by virtue of me having this density function, if I want the probability of seeing a big gap, say bigger than t, I just have to integrate the interval t to infinity against my density function. And when I do this, I'm able to show that I have kind of quadratic asymptotics. So the probability of seeing a big gap bigger than size t is about 1 over t squared. So this is very tiny. But when we again compare this with the IID case that has exponentially small gaps, we're able to see that large gaps are unlikely in this case, but it's still much more likely than the truly random case, right? So we have a very big tail in this context. And kind of the other side of the token is if we look at big gaps, what about small gaps, right? And so we remember kind of from the picture that there's kind of, it's kind of a constant function, which is kind of another way of saying that if I want to look at a small gap, say smaller than epsilon, again, I just have to take the interval from 0 to epsilon and integrate this against my density function. And no matter how small epsilon is, I'm going to see a positive proportion of gaps inside of that interval for every epsilon. Okay, and so this question about small gaps is really interesting because actually we would expect that there's support at 0. We expect, for no matter how small epsilon is, we're going to see a positive proportion of gaps because double slit tori in general are not lattice surfaces. All right, so lattice surface I'll kind of get into very shortly, but it's kind of telling us there's a lot of symmetries. There's a big group of symmetries of these translation surface. So it's a very geometric property. And by a result of a Thread-Shaika that I'll mention shortly, it turns out that not being a lattice surface, not having a lot of symmetries is exactly the same thing as having support at 0. So we actually already knew this about double slit tori by a result of a Threya-Chaika, but this kind of gives us another proof of the fact that a double slit torus is not a lattice surface. Okay. And so, double slit tori are great, but it's a very natural question to see what we can say in higher genus. And so in higher genus, we can do a similar construction. Instead of taking 2 identical tori, let me take the identical tori, and let me each glue them along the same slit. Up to reordering, I'm able to just show that the permutation that I'm gluing them by is given by the following, right? So if I'm on this first torus and I hit 1, I come out of 1 and I'm over here. Maybe I cross this side right here. So I come out of the other side, cross through 2, pop out to the third torus. And so this class of translation surfaces are called symmetric torus covers. And we can ask about the gap distribution of a symmetric torus cover. And it turns out that symmetric torus covers actually have the same gap distribution as double slit tori. So in some sense, kind of 2 is the same thing as bigger than 2. And so that kind of concludes maybe the first part of the talk of kind of my results. And so for the second part of the talk, I want to kind of review some of the history of gap distributions, including some results in the torus, as Dimitri asked about. And I want to walk us through some elements of the proof. So maybe I want to stop here and see if there are any questions from anyone.
Anthony,
Mhm.
do you get anything different if you just look at closed saddle connections versus all?
I think if we look at just closed saddle connections, I think this is going to just recover the results of the torus case, because in this case, kind of the saddle connect. So for the people who know something about double slit tori, the saddle connections in this context come in 2 flavors, right? They're either closed, in which case they look like the primitive integer lattice. And those kind of gaps of this set are very well understood by results of Hall. And it's the fact that I'm looking at non-closed ones, I'm looking at saddle connections between dot to x and x to dot, that give rise to a new interesting thing that's happening in the saddle connections. So in the case of just closed ones, I think we understand them by previous results.
And is that the same if you look at like higher, like the other degree torus covers? Like, just look at the closed ones for symmetric torus covers, for instance.
I think so. For the same, so you'd have to double check that again. This is just the kind of visible. This is just the primitive integer lattice again, right? But kind of like the only way it wouldn't be is if, like, when I crossed through the slit, I had some extra room to wiggle around and get something different than a primitive integer vector. And I think the only way, once I cross through a slit, the only way I can close up again is by kind of finishing the one that would have started, that I would have, like, what I'm trying to say is if you kind of project this down to just a single torus, you can see quickly that all of them are still going to be primitive integer lattice vectors. Yeah, it's a good question though. Are there any other further questions? And if not, then I'll kind of survey what we know about gaps in the context of translation surfaces now. So I'm not going to split this up kind of chronologically. I'm going to break it up essentially into 2 parts. One, kind of the lattice surface case, so kind of highly symmetric translation surfaces, ones that have lots of symmetries, like the regular octagon or like the torus, and then non-lattice surfaces that don't have a lot of symmetries, like double slit tori. So in the context of gaps of lattice surfaces, kind of the first explicit gap distribution computation was done for the torus by a Threya-Chaika, right? So again, what this means is we're taking the torus and I'm looking at saddle connection paths on the torus, and then I'm looking at the slopes of those saddle connection paths. It's not so hard to see that these are just recovering the Fairy fractions, right? So understanding the gaps of saddle connections of the torus is one and the same thing as understanding the gaps of Fairy fractions. And it turns out that this work in 2014 recovers results of Hall from the 70s, where he computed a gap distribution for Fairy fractions and showed it has kind of, it has a quadratic tail, for example. the really interesting thing about the Atreya Chaika work is this is, Hall's work is purely, is kind of analytic number theory work, okay? Atreya Chaika is able to recover the exact same result using dynamics in the space of lattices. And so it's really interesting that they're able to kind of recover this work in this context. And it's led to a lot of other work, including gaps of other lattice surfaces like Atreya Chaika Lelievre, where they studied the golden L. And so by the golden L, I mean kind of this surface here. So where phi is the golden ratio. So phi is the golden ratio and phi bar is 1 over the golden ratio. Shortly thereafter, Ionic work looked at the gaps in the context of regular octagon. And then very recently, Taha looked at gaps of kind of gluing 2 regular 2n+1 gons. So this is kind of what we know about gaps of lattice surfaces. And some common characteristics about these are, in each case, there's no small gaps. Again, this is not surprising given by a result of Atreya Chaika that I'll get into shortly. In all of these cases, the parameter space is somehow 2-dimensional. And in all of these cases, except the Taha case, there's an explicit gap distribution. So we're able to, full on understand the density function in all of these cases. And so we can move on to the world of non-lattice surfaces, where kind of the first result in this direction was by Atreya Chaika that was looking at generic translation surfaces. So they show that for the gap distribution exists for almost every translation surface. Generic here again, almost everywhere in generic means with respect to the Maser-Beach measure. They show that it's actually the same gap distribution for a generic translation surface. They show so because of the fact that they're talking about a generic set with respect to Maser-Beach, their results are very non-explicit. And in spite of the fact that they're kind of talking about a generic translation surface with respect to Maser-Beach, they're still able to show this characterization that I've been hinting at for many slides now, that small gaps characterize non-lattice translation surfaces. So this is like, I really love this result because it's saying, whether it's a lattice surface or not is a very geometric thing. And I'm able to kind of characterize this geometric thing by looking at the gaps of saddle connections, and in particular, looking for small gaps. And I think that's very non-obvious, maybe at first glance. And shortly thereafter, work looked at another genus 2 class of translation surfaces given by the ones that have a single cone point, right? By double slit torus have 2 cone points in our genus 2. So work kind of looked at single cone point genus 2. And in her situation, her parameter space was very high dimensional. It was 6-dimensional. So she has some upper bounds, but it's not explicit, her density function. She has some upper bounds for it. And then where my kind of work fits into this context is the parameter space of double slit tori is somehow 4-dimensional, and it's an explicit gap distribution for a non-lattice surface, and as such is the first explicit gap distribution for a non-lattice translation surface. And so now that I've kind of walked us through my results, I've walked us through somehow what we know about gaps in the context of translation surfaces. I want to leave us with some sense of how you prove a result like this. And the way you prove a result like this is actually, very, very powerful technique and borrowed from homogeneous dynamics that was, sent to the world of translation surfaces, that questions about a fixed translation surface can be understood by considering dynamical questions in the space of all translation surfaces. This kind of guiding philosophy, right? And so there's many instances of this philosophy. Maser's criterion relates kind of unique ergodicity of the vertical flow on a fixed translation surface with kind of the geodesic flow of the ambient translation surface in the moduli space of all of them. Veitch's dichotomy again does something similar. We can understand whether a lattice surface has optimal dynamics by understanding its SL2 orbit in the space of all translation surfaces. So this work of gap distributions is actually another instance of kind of this guiding philosophy. Very important for me to say, I did not create this instance of this philosophy. I was very fortunate that many other kind of people were able to work on this and see this instance of this philosophy, that I can relate the gap distribution to a dynamical question. People like my advisor, Jayad Atreya, people like Yi-Chua Chung, John Chaika, Samuel Lelievre, were able to kind of notice this philosophy. And what I want to walk us through at the end of this talk is what this instance of this philosophy is. Okay, so more specifically, I'm going to teach us how we can go from a gap distribution question for a double slit torus to a dynamical question on the space of all double slit tori. So let's start to formalize some of the ingredients that we have here. Let denote the space of all double slit tori by script E, right? So here, two examples of double slit tori, and these are both elements inside of E. And this is a very nice space, right? But right now this is just a very static space. So let me introduce, I keep talking about the dynamics in the space of translation surfaces. Let me introduce finally the dynamics here. So there's a very natural linear action of SL2R on the space of double slit tori, right? An element inside of here is given by a polygon, right? So I can take a polygon, an element inside of, E, and I want to know how I can act on it by a matrix. Well, I know how a matrix acts on a 2D picture, so I can just do this to this picture here. And maybe there's questions, right? This picture, the surface that we're starting off with on the left has some identifications, right? And so one may worry about the identifications after we apply a matrix to it. But all the identifications are by translations, right? All the identifications are along parallel lines, and acting on it by a matrix preserves the notion of parallel lines. So we get a well-defined kind of surface after we act on it by a matrix. And this is what I mean by the dynamics in the space of translation surfaces, or the dynamics in the space of double slit tori, just given by the natural kind of linear action of SL2R on the polygon presentation. And out of SL2R, I want to consider the following one parameter family of matrices that I'm going to call the horocycle flow, given by the lower unipotent elements. So some things to kind of note here are the horocycle flow is the lower unipotent and not the upper unipotent, and I'm parameterizing it with negative time. And hopefully, you'll see, I'll start to kind of hint at why I want this horocycle flow. Okay. And why it's a good kind of one parameter family of surfaces to consider in the context of gap distributions. So some kind of obvious remarks here are the horocycle flow is a vertical shear on the plane, right? Kind of vertically shears things, and the subgroup is of interest to me because of how it changes slopes. So what do I mean by this? Pretend I have some just arbitrary vector xy, and I act on it by the horocycle flow. Then I'm going to get the following vector in R2. And so if I take the slope of this vector right here, I'm able to relate it to the slope of the original vector before I flowed it by the horocycle flow. Namely, I get the slope of the vector pushed by the horocycle flow is just one and the same thing as the slope of the vector minus the amount of time that I've flown by. Okay, so in particular, if I'm interested in gap distributions, in kind of gap differences, then the horocycle flow is very natural to consider because slope differences are being preserved. Right? So this is one reason why I would want to think of the horocycle flow in this context. And now I can start to build up some kind of more formalism to tell you what this dynamical question on the space of double slit tori is. Let me consider the following transversal for double slit tori. So in words, this set is just a set of double slit tori that have a short horizontal saddle connection. Short for me here means less than or equal to 1. Okay? So let's look at a picture of this. I grab a double slit torus, I look at its saddle connections, and I say it's inside of W if there's a saddle connection inside of this set right here. So since this saddle connection lands inside of the interval 0 to 1, I throw this inside of W. Okay? And so I have this word transversal here. So what do I mean by kind of a transversal? I mean that this set is somehow lower dimensional in the following sense. In the following sense. The picture to have in mind, by the way, for a transversal is some kind of lower dimensional subset such that once I take an element inside of there and I flow by it by the horocycle flow, I immediately pop out. So how do I know I'm immediately popping out of this set? Well, if I have a short horizontal vector, once I apply the horocycle flow, this is going to shear things down. And by discreteness of saddle connections, it'll take me some time before I get another short horizontal vector. So this is what I mean by kind of transversal, and why I'm thinking about W as kind of a lower dimensional subset. Okay. And the key idea to turn the slope gap question to a dynamical question is to realize that slope gaps are actually one and the same thing as return times to W, right? So what this means, right, is if I take something inside of this transversal, I can ask, when's the next time I come back to this transversal? So unpacking what this means, I literally need a vector inside of my saddle connections so that after I apply the horocycle flow, I get the following vector. And I need this vector to be short, and I need this vector to be horizontal. So short just means that this vector needs to be between 0 and 1. And horizontal means that I need this to equal 0. So in order for this to equal 0, I realize that I need a flow by a slope. I need a flow, the amount of time I need to flow by is a slope of a saddle connection, right? So if I want the first return time, the slope that I'm looking for is the smallest positive slope here. So if this is 1 and this is 0, in order to come back to W, I need a vector that to land inside of this interval here. So the horocycle flow on this picture kind of shears everything vertically down. And so I can see that the next time that I get kind of a vector inside of here is going to be this vector. And I need a flow by its slope in order to land inside of here. So what is this telling us? This is telling us that kind of the first return time is a slope, right? But we're not actually interested in slopes, right? We're interested in slope differences. So what about the second return time? And the point is, there's not that I can run the exact same argument I just did, right? In order for me to have a vector, a second return time, it means I need a vector to land inside of the interval 0 to 1. And I don't want the first vector to do that. I want the vector with second smallest slope to do that, right? So I want this vector in this context to do it. So the amount of time I need to flow before I get a second return time is going to be given by its slope, given by S2, let's call it. So that's not actually, S2 is not actually the second return time. S2 is the amount of time I need to flow in order to come back to the transversal twice, right? If I've come back to the transversal twice, that means I've come back to it once before. So S2 is kind of the total time I need to flow by. And the first return time, as we saw in the last slide, is S2, is a slope given by S1, say. And so the second return time is a slope difference, as I was kind of hinting. So the second return time is a slope difference. And now let's kind of formalize, let's kind of bring everything together and formalize this kind of key idea here. So let me let R denote the return time and T denote the return map under this transversal. R is just the function that the amount of time I need to wait before I come back to the transversal. And T is just the return map, right? So it's kind of implicitly defined by flow until I come back. Well, now that I've kind of flown until I've come back, then I've come back to the transversal. So kind of pictorially, what's happening is the following. I have my transversal W, and I have some element inside of here. And then I flow by it, and I immediately come out of this set. And maybe I flow and I do something interesting. And then when I come back, that's what I'm going to declare to be T of W. So it's this induced dynamical system out of the transversal. And somehow the length of this chord is what I mean by R of W, the return time. So this is kind of the picture to keep in mind. And so now with all these ingredients, we can finally start to piece together, right? Slope gaps are return times to the transversal, right? Which is another way of saying, slope gaps are, the return times to transversal. Again, remembering what we've done earlier, when I is equal to 0, I get S1 is equal to R of omega, which is just saying the return time is a slope. When I is equal to 2, well, when I is equal to 1, I get S2 minus S1 is equal to R of T of omega, which is saying that the slope gap S2 minus S1 is the return time after I've come back, which is another way of saying the second return time. Okay, and so now with all these pieces there, I can finally recast the slope gaps question as a dynamical question, right? So this is not exactly what this kind of quantity that you see here is kind of like the gaps up to n that land inside of my favorite interval out of how many of them could have landed in there. So many of you will notice this is not exactly looking like the same quantity that I defined earlier. There's like a kind of second renormalization I have to do by the diagonal action that I don't want to get into, but morally speaking, the quantity I have up here is essentially the same thing that I talked about at the beginning of the talk. So kind of there's kind of like a warning, I guess. There's a small, very small lie here. And so now I know something. I know slope gaps are the same thing as return times. So I'm able to rewrite this quantity as the following sum, right? So there's a lot to kind of unpack here, right? If I want a return time inside of the interval I, that's what this is tracking right here. And I want to do this for all of the times that I've returned. And that's kind of what this is tracking here. So every time that I have a slope difference, I want this bell to ring. And this is being captured in this indicator function on this kind of sum of this induced dynamical system. So this is always my favorite part of the talk. Unfortunately, I probably won't be able to surprise anyone here today, but this is my favorite part of the talk because, if I'm not at a dynamic seminar, everyone kind of looks at me like I'm crazy at this point, right? Because I've taken this perfectly innocent question of slope gaps and I've turned it into this, indicator, this sum of indicator functions on this kind of induced dynamical system. And it doesn't look like I've helped the case at all. But because I'm talking to a bunch of dynamicists today, everyone sees this and they get immediately very happy, right? This is a Birkhoff sum. So now I'm able to understand kind of the slope gap distribution by using methods of ergodic theory, by using kind of dynamical techniques of ergodic theory. And Birkhoff in particular tells me that I know a lot about this kind of sum right here, that kind of assuming I have some kind of ergodic measure that I'm kind of pushing under the rug, but please ask me if you want. I know what this sum converges to as n tends to infinity. This is going to converge to just the integral of this function right here. The integral of an indicator function is its area, and then I just kind of rewrote the inverse image kind of explicitly. So now I've reduced the question of slope gaps into a dynamical question on the transversal. W, T. And this kind of hints to you, this closes, first of all, this instance of this philosophy that I can turn the question about a fixed dynamical system into a dynamical question in the space of all translation surfaces. And it kind of hints to you what the next steps are. I need to kind of parameterize W explicitly. And after I give it coordinates, after I parameterize W and give it coordinates, I need to kind of find the return map to compute this kind of area. So this is all I kind of wanted to share for us today. Just wanted to walk us through, slope gap distributions for double slit tori, which constitute the first explicit density gap distribution for a non-lattice surface. And then I wanted to walk us through the history of gaps and translation surfaces. And then lastly, I wanted to finish with a kind of an element of the proof, how one turns this slope gap question into a dynamical question. So I just want to say thank you to everyone for showing up. I want to give special thanks to my advisor, Jayadev, and to the New England Dynamics and Number Theory Seminar.
Okay, everybody, why don't we thank Anthony? Virtually or really. Are there any questions? Well, maybe I'll jump in with one. Can you hear me all right?
Yep.
If instead of gap distributions, you looked at pair correlations for the statistic for the slopes, are there results for that? Is this done?
I don't know, to be honest. I don't know if there's any kind of results for just the pair correlations, right? Because here we're not looking at all kind of differences. We're just looking at consecutive ones. Mm-hmm. Yeah. So off the top, it's a good question that I don't know.
All right. So can I ask just a couple of quick questions? Mm-hmm. So just to summarize your historical interlude, one thing that I got out from it is that lattice and non-lattice surfaces behave in a different way. Mm-hmm. And for lattice surfaces, this is well understood. Just for an arbitrary lattice surface, or for some examples of them, what's the situation? There is a distribution. I mean, no matter which lattice surface you take, this gap distribution is known, or it's not true?
So for a general lattice surface, it's not known, but like this kind of element this kind of method of proof that I've shown you here should generalize relatively well to lattice surface. And in fact, kind of the work of Chalar and Grace, of Ionic and work, for the octagon, in their paper, they actually give a kind of, Poincare section for a general lattice surface. So using this for any kind of fixed lattice surface, you're able to kind of push this machinery to compute the explicit gap distribution. But as like a very simple question, we don't know what the gap distribution is for like all square tiled surfaces. Although there's like kind of work being done in this context, we don't know kind of any characteristics about this.
I see. Okay, but I mean, if if there is one thing I understand, mm-hmm. It's probably what happens with the standard integer lattice, or the saddle connections in the torus.
Oh yeah.
And there are two features, right? So first of all, rational points repeal each other. So if you have Fourier fractions with denominators up to n, mm-hmm. It means that you cannot get gaps smaller than 1 over r squared or n squared.
Yeah.
Right, and this so there are no basically there are no small gaps.
Mm-hmm.
Right, and this is not true for non-lattice.
Exactly. Yeah, this is a consequence of a Triachaika that you can characterize lattice surfaces by whether they have small gaps or not. Exactly. Yeah.
Okay. And as far as large gaps go, I mean, if you look at again, if you look at all rational points with denominator up to n, then you know what is the largest gap. It's from 0 to 1 over n. And there is nothing larger. So in this sense, it's not random.
Yeah.
I mean, it's not possible to have everything in below 1/2, so that we have a gap of 1/2, basically. So the probability is 0. And you're saying that for non-lattice surfaces, it's not true? That you have...
that you have arbitrarily small gaps?
No, I'm talking about...
or big gaps?
Gaps. So what about the large gaps? You can...
So we don't know.
Upper bound on the biggest gap?
No, yeah, we don't know this either. So like for a generic kind of translation, surface, we don't know what the probability of having a large gap. But I think this is like a super interesting question actually. And I thought about it a little bit. So Jayade, for example, has kind of gone. He's kind of conjectured that maybe it's quadratic, and then he's kind of recently kind of stepped back from this conjecture. So it's unclear whether it's like the decay is quadratic in this context or not. But it's a very interesting question.
Okay. And so maybe the last question, as a person coming from the homogeneous dynamics world, you can also take the two-dimensional torus and generalize it to be a k-dimensional torus. And then you have rational lines and some kind of multi-dimensional slopes of rational lines. So is there such thing as this multi-dimensional gap distribution?
So there's not actually. So I remember actually some time ago I gave a kind of similar talk on affine lattices, right? So this work actually is building on the work of affine lattices that I've done to double slit tori, and a lot of this work is kind of very two-dimensional specific. But I do think there is some. So the current state of the art is that this is purely two-dimensional. But I do think there should be some kind of possible things to do. For kind of higher dimensions. We don't have any kind of explicit things in this context yet.
But just capitalizing on my question, just think in terms of this philosophy. There should be this multidimensional horocycle flow acting on the space of lattices, and maybe something reduces to some recurrence questions of this horocycle flow, but it's not something Jayade or John or others.
No, it's not something that anyone's kind of like that I've talked to has kind of talked about, and there's certainly nothing written. But I think it's a prime area to kind of look at something.
Okay, wow, that's interesting.
Because especially like in kind of the context that you were looking at, for the lattice surface case, kind of the parameter space that you end up looking at ends up being a homogeneous space. So if like for example, you're interested in so maybe you're interested in kind of the algebraic integers of like q adjoint square root of 5 or something like this. This is kind of very intimately related to the golden L, and there should be something related to this, in higher. You can easily generalize this question into higher dimensions too. So I think there's some things that can be done there.
Okay, thanks.
Thank you.
Are there any other questions? Well, if not, why don't we thank Anthony again and conclude the official part of the seminar.